Okay, perfect. All right. Okay, so yeah, so again, I'm Dan Kilper from Trinity College Dublin, and I'm going to talk to you about the 6G-XCEL project. 6G Transcontinental Edge Learning is the project. Oh, we're not hooked up on this. Okay. So it's basically an EU-US cooperative project on AI for 6G, and it started in January. So we're still ramping up a bit and getting things going. And it's a 3-year project. Basically, we've got 10 EU partners. I think everyone is represented here in the room. And we identified opportunities for 10 US partners. And across both the EU and the US, there's 9 major initiatives that we're bringing together in this. And the 6G-XCEL, the funding is on the EU side, so there's a consortium over there. There's still talk of opportunities where NSF is trying to line up some money on the US side, but we're looking to find ways to partner and work with other initiatives on the US side and see what we can do. And that's part of the motivation for the workshop here. As we developed the program for 6G-XCEL, we noted that there's this kind of fragmented network AI environment, especially when you're thinking about end-to-end. You've got radio and optical, and they're somewhat siloed research communities and activities going on there around AI. If you think about if you want AI to go from the hardware devices, you've got radio elements and controls, you've got optical transceivers, and then you go up to the switching layers, and then the higher layer network control, and then back to the data center and the softwareized network functions. And so you need some sort of consistency if you're talking about AI for network control end to end that goes across what we're referring to as north-south from the hardware devices through to the softwareized network functions. And you also need this kind of east-west sense of AI coordination across different types of networks, across different domains, between the RAN and the transport, and across multiple operators. And we identified for this project that there's significant interest in trying to understand how AI can be implemented across this environment, what the challenges are, and how we can overcome those. And so that's really what went into the 6G-XCEL vision. So in focusing on edge network use cases and decentralized multi-party AI controls running over edge compute to coordinate control across radio and optical networks, and develop a framework for AI and 6G. So a framework, not to be prescriptive and say, okay, here's an AI control plane, this is the way it is, everyone needs to do this, but to get a framework for studying and understanding this kind of distributed AI control and pave a way towards validation, adoption, and standardization of AI approaches. And we refer to this as decentralized multi-party, multi-network AI framework, or DMMAI, we're calling it, framework. And we want to enable the federation of AI-based network controls across physical layers, and develop reference use cases, data acquisition, generation methods, data and model repositories. And then also, but 6G-XCEL is looking to bring together a large ecosystem of researchers from the EU and the US to implement elements of the DMMAI framework in their test beds and labs, integrating it into their existing research programs and validating the framework across platforms. So again, it's not that we're trying to come up with a large research program that's going to implement this and that and drive it all forward, but we want to build tools and study these types of interfaces and then work together to implement them across the various projects that we all have going on in our initiatives and centers and programs, and work openly across continents to closely with standardized groups within each jurisdiction. And again, I want to emphasize, so we're looking at this decentralized multi-party, multi-network. Multi-network here refers to both multi-domain and radio and optical, so multi-technology networks. And then this idea of bringing together this ecosystem and really in thinking about test beds in a big way. So this is a quick example. So if you think about a kind of an ORAN type environment, you have various AI data and applications at the edge. You've got your RU, DU, and CU in your radio access network. and running this through your various SMO and RIC elements across these various network elements. Now, um, my background, many of you know, is primarily in optical networks, and I've been really interested in this from a radio perspective, and then trying to understand, okay, well, what about in between each of these points? So there's actually optical systems in between each of those network elements that are implementing these radio functions, right? And so if I want AI control end to end and supporting AI applications at the edge, I also need to think about that aspect. And in particular, one example that we were thinking about is kind of real-time vehicular traffic management, going beyond kind of the type of thing that you have on Google Maps or something that gives you updates, but it's not real time, and it's not taking advantage, let's say, of video, and it's not controlling intersections and really trying to manage traffic in a deeper way than we have today. You can imagine that if there's some sort of congestion or problem, that there'd be a large number of devices that are working with that environment, and as well as all the vehicles trying to move data to, let's say, AI at the edge that's going to inform that and try to resolve whatever the problem is in rapid time. And so you need this kind of control loop at the edge where you're pulling data and then responding and trying to control traffic lights and other things. And you might imagine that you'd want to turn down certain radio antennas that aren't needed to provide extra capacity over in the areas where you do need that, and also you want to perhaps move or adapt your optical capacity in response to this, as well as maybe moving some of your AI resources to the edge to support some sort of event like this. And of course, well, why do you want to do this? I mean, so one solution here is that I could just deploy massive capacity everywhere, massive compute everywhere, and I don't need to adapt at all, right? And so the question is, why? One of the clear reasons why you do this is this was a recent report about Google and how their emissions are climbing 50% in 5 years due to AI energy demand. At the end of the day, we can't just throw capacity and compute at all of this stuff. We do need to think about being efficient and how we can optimize our networks to be able to support all of this functionality at the edge. All right, so the challenges to multi-network AI controls that we've identified here is, well, there's conflicts between AI controls running in different domains and technologies. And I know this is something that's receiving a lot of attention right now, this issue of competing AI controls in a network. Also, there's maintaining security across the different networks, right? Preserving privacy of both the applications and the networks, ensuring overall energy and resource efficiency, achieving fast and reliable control loop response times, and of course, scalability. And each of these, we've got programs within the 6G-XCEL project where we're trying to understand and make progress on these. So when we look at kind of the RAN and the transport environment, this is one of the kind of proposals about how the RAN, say, RIC type environment and SMO type environment might work with the transport software-defined networking environment. And it's really kind of a bolting together of these two control frameworks, whereas in the one world you have this kind of SDN control environment, in the other world you have RICs and SMOs, and you've got this nice multi-layered hierarchical control framework. And the concept of a RIC. I guess it was a year and a half ago now, I was at the Optical Fiber Communication Conference, which is your top optical conference, and there was a big workshop on AI for optical networks. And I asked the folks at the workshop, how many of you have heard of a RIC? And these are people from major optical transport vendors and network operators. And no one on the panel had heard of the term RIC before. Okay, it's really illustrated to me how siloed these communities are. And here they're thinking about AI controls in the orange part of the network here, and not understanding at all what's going on in the radio side of things. So we really need to understand how these would work together. And so what we wanted to do in 6G-XCEL is, so we create this framework for understanding how your non-real-time RIC, your near real-time RIC, your network OS, and your transport SDN, how they might all work together. And so we're not going to change the architecture of the network or propose that overnight or anything, but can we look at implementing common elements across all of these, right? And then understanding if we're going to get them to work together, what are the bottlenecks there, and how can we do that most efficiently? And importantly, like AI service management and orchestration, we put completely outside of this. We assume that that's something that many folks are working on and going to develop their own solutions there. But ultimately, those AI services and that orchestration needs to work across these different networks and these different controllers. And so how do we understand how they might interface to this? And so we're kind of looking in a service management and orchestration agnostic approach. Of course, we're going to look at implementing a few AI service management techniques and use those for studying this DMMAI framework. But the intention here is to not be prescriptive about this. So we take this kind of generic view of an AI controller as a toolbox that has various repositories that you need of network data, abstracted data. You need some sort of curation and DSP on data. You need a north-south communication ability and east-west communication among the different controllers. And you also need repositories for models, and you need some sort of policy supervisor or management and other testing and validation for your elements as well. And there's an assumption that you also have user resources, and you'll have third-party AI apps and so forth that are all kind of outside of this controller, but would be interacting with it and thereby controlling the network. So we've introduced an initial kind of architecture for the DMMAI framework, which is a publish subscribe architecture. This was primarily developed by Miriam, who unfortunately isn't here, but he's going to be online later this morning to talk about this. And basically it consists of message brokers for your local control, as well as your inter-AI east-west communication. And then there's a set of XApps, your AI-powered control engine, and a protocol translation module and other node controls. And here's kind of the layout of that. So we have our apps on the left-hand side with your AI controls that people can then bring into the network and register with this register control framework in the middle. That basically one of the important things there is it has performance management and control capabilities. So it'll detect if there's conflicts between the different AI controllers and flag that for us. And so you can implement various AI contention control mechanisms within that framework. And then we have these message brokers, right, that handle the east-west as well as north-south and local controls within the node. And so just as a quick example, so when a network node comes along, it will register its capabilities, what its performance metrics are and control parameters, and then it'll get registered into the system and make that available to the brokers. And then various AI control applications can come in. And for example, here we have the first application comes along, and it needs certain capabilities and performance metrics exposed to it. If it turns out that those aren't available, then the registration would fail, and so it'd be backed out. On the other hand, with application number 2 down here, it registers itself, check the information, it looks good, so it becomes registered, and now it can start basically reading the performance metrics and controlling the node or the various elements there. Yeah. And we initially looked at this in terms of we had a demo that we ran at this OFC conference that involved both a RAN implementation, basically an ORAN implementation, and a PON implementation. And there's a CTI controller that allows you to influence the dynamic bandwidth allocation in a PON controller. And so this is our passive optical network and our radio network. So we've got the pawn in the middle, and we need the pawn to be aware of what you're trying to do in the radio network and the certain latency constraints and other things associated with that. And so the idea is that we implement this AI controller now in the pawn and in the ORAN environment. And then we have also the communication protocols to allow these to communicate with each other and manage this network. So this is the direction that we're moving forward with this type of approach here initially, as an example. And then, so if we go back to the previous application example, I put my AI controller now in the various nodes, both optical and radio. And the idea is that they can now communicate with each other and coordinate AI end-to-end across these various elements. Right. So that's the important thing. Now, how are we going to implement that? Well, again, our intention here is to be agnostic to these kind of implementation aspects and so forth. And so we have Juniper as a partner in the program. They actually have a nice ORAN SMO and also transport network SDN environment. So they've got a production solution to much of this. And we're going to look at now implementing this DMMAI framework or the AI controller, both as XApps and RApps, depending on which capabilities we're looking at. And then also there is the opportunity to even put it natively in the, is there a laser pointer here? No, I guess not. But there you can put it AI, you can put it natively in the elements here, although perhaps there won't be any performance difference between the two. There's also at Trinity, we're building, for example, our own custom RICs, and there's other open source RICs and transport SDN environments. And so the idea is to also have open source implementations that will be used. Also at Patras is developing their own open source custom controllers. And so we'll have toolkits that we can use with these various control environments. And so that each test bed can integrate these types of controls with their own capabilities and in their experiments. Now we have two main use cases for the purposes of studying this framework that we're looking at in the 6G-XCEL project. One would be managing energy use across the network, and the other is spectrum management use case. And we'll be talking about those more tomorrow during the session. And then the idea, so we have the Open Ireland and Patras 5G PNet test beds are kind of the main test beds where we'll implement the use cases and we'll call it full implementations of the DMMAI framework. And then working with Cosmos here, CCI at Virginia Tech, Slices in the EU, and various test beds that they have here, as well as City Lab and the IMEC test bed at out in Antwerp. And so, and in these other cases, we might not implement the full DMMAI framework, but different elements of it that are useful to study for the various experiments that these test beds have going on in their environment, right? And see how we can benchmark across them and make progress there. So again, now we want to understand how different control architectures will impact performance and stability. We've introduced this first publish and subscribe architecture, but we want to look at others as well. Gain an initial understanding of security, privacy, and energy efficiency implications. So we have various work packages specifically on each of those to understand how they are impacted by how you implement some sort of controller like this, and develop methods to study and test end-to-end AI in network control, including benchmarking, develop data and tools, and then bring together research communities across the EU and US and radio, optical data, AI, compute, applications, security, privacy. So there's a very diverse group of disciplines involved here that we want to engage in this effort. Okay, and that's 6G-XCEL. So thanks for your attention. Any questions? I mean, I guess it varies by component. I mean, generally, in many of our test beds, we have custom let's say, a custom receiver that we've built ourselves, and there you can control virtually every aspect of it. We also have cases where we have a transceiver, for example, that was built by a company called Lumentum that goes into a switch box, and that type of controller will have certain controls exposed to it. Usually something like you can set the baud rate or the modulation format of these optical elements and so forth. And so, and usually there's some sort of interface that allows you to do that. We can expose that to these AI controllers depending on the need, right? Now, in general, we don't design a software interface that exposes every feature of a transceiver to our SDN controllers, let's say. But we generally pick whatever controls we need for a particular experiment, and we can expose it, and on a as experiment needed basis, we can add finer granularity and controls that way. Yeah. So in an experimental sense, you can really get as granular as you want. In the real world, so the system vendors, they don't like to expose their controls to the network operators at all, right? So I think it's very limited what they have available. Questions? All right, so